Good evening and welcome to Lowell Observatory's ongoing coverage of the Lowell Discovery Telescope as we celebrate the 10th anniversary since first light, when the telescope was first used to do research. And boy, talk about going fast. 10 years has passed already, and there's been so much great science that our scientists have done with the telescope. But when I say our scientists, I talk about Lowell Observatory, but Lowell has several scientific partners, institutional partners, with the Lowell Discovery Telescope, or LDT as we shorten it. And we've spoken with several partner organizations this year. And tonight we've got a group from University of Toledo. And you know that we were just talking about Ohio and Toledo, and me growing up and doing fossil collecting there because it's classic fossil sites. And of course, Jamie Farr, I guess this is maybe too old, but back when MASH was on, the TV show, and Klinger always made a big deal about being from Toledo and the Toledo Mud Hens. And so there's a little bit of Toledo and culture, but Toledo, has an outstanding astronomy department, and some of the work that's being done with the Lowell Discovery Telescope by Toledo faculty and students is just remarkable. And so we're going to hear about some of that tonight. Originally, we're going to talk to Antoniu Fodor about his research, but because this is a lot of fun, I think this is the reason, not any coercion, that a couple other of your fellow students are going to join us, Grant Donnelly and Sam Federman. And so we're going to hear from each of them, their research, how it ties in with Lowell Discovery Telescope, and talk about what they're working on and what their goals for the future are. They're all graduate students, and probably are starting to think there's a light at the end of the tunnel of your studies, and hopefully it's not an oncoming train, but is actually, you're soon finishing with that stage of your careers and moving on to the next stage. So let's start with you, Antoniu, and we'll hear about your research a little bit. And just a little bit of background, Antoniu is a fifth-year graduate student at University of Toledo, works with Dr. Ann Medling's research group studying how fueling and feedback affect galaxy evolution. And to answer this, he's leading an observing campaign with the LDT to investigate why some galaxies have recently stopped forming stars. And so I'll turn it over to you, and let's hear a little bit about your research and how the LDT is important for that. And before I do that, let me just mention for those watching, for our guests watching, throughout the night, if you have any questions, send them in the comments in the YouTube feed, and our crack behind the scenes team of Maddie Mooney and Nate Nice will share those, and we'll get to questions kind of as we can, and when the timing is appropriate. So, this is interactive as our viewers would like. So if you have questions on specific research or about our presenters in general, just send them in and we'll try to get to them. So with that, Antoniu, I'll turn it over to you.
Sure. Hi, everyone. As you mentioned, I'm Antoniu. Today I'll be talking about my research looking at shocked post-starburst galaxies, which are a really interesting sample for us to study in terms of galaxy evolution. Before I begin, just want to shout out all of the amazing undergraduate researchers who have helped me so far with both remote observing, prepping targets, data reduction, and data analysis. Some of whom, Thomas and Alex, I think because of their experience working with the LDT, have moved on to become telescope operators at UCURT. So super happy for all the work that they have helped me with.
Try clicking. Oh no, you can use the mouse too. Yeah.
Okay, so when we talk about galaxy evolution, the reason we talk about it is because we see two main groups of galaxies in our local universe. First, we see red elliptical galaxies. These are more spheroidal, they look like spheres, they have little to no molecular gas inside of them, and they have little to no new star formation. That's what causes these redder colors, because there are only older stars inside of them. Juxtaposed to that, we have blue spiral galaxies. These have more of a disk-like morphology. They have a lot of molecular gas inside of them, which allows that gas to condense down and to form new stars. These young stars is what gives blue spiral galaxies their blue color, as you can tell from that image. So over the years, astronomers have really come up with this conclusion that galaxies have to evolve somehow through different pathways from blue spirals to red ellipticals. The process of which we don't know for sure and is an important question in astronomy. We do know some things though. Generally, when they evolve, gas has to be used up or it has to be lost. The way that gas can be lost is from feedback, where you have some powerful mechanism in the galaxy pushing gas out. So there was no new gas for stars to form and condense down from. Additionally, star formation can stop through a process of quenching. Think about when you quench your thirst, you stop feeling thirsty. When star formation is quenched, there's no new star formation. So one or both of these happens in order for galaxies to evolve. One important physical mechanism in these galaxies that we are looking at when we consider galaxy evolution is black hole and black hole feedback. It's the black hole in the center. They're thought to be one of the main contributors to galactic quenching. So normally for the black hole, you have gas and dust accreting onto an accretion disk around the black hole, feeding into it. Occasionally, the black hole becomes highly energized and pushes out these large-scale galactic winds that are potentially quenching galaxies by energizing the gas and heating it up, or by removing it from the galaxy. So we're really interested in finding out more about black hole feedback. So the main quenching approach theory that we're looking at is this inside-out quenching model, where you have a blue spiral galaxy, and over time, the center gets quenched. And you see a difference in star formation in the center, and there's still normal blue star formation on the edges, and it expands outwards radially. Here on the right, I have a color plot versus galactic mass that shows, again, just this bimodal concept that you have blue spiral galaxies and red ellipticals. And we believe that there's just some different pathways by which a blue spiral becomes a red elliptical. What we really want to look at then is galaxies in the region between the two. Unfortunately, it's a lot more rare to find something in this green valley, which is why we call it a valley, because there's only a few galaxies there. So when we look at galaxy evolution, we really try to aim for some target list in that group. These are known as post-starburst galaxies that we mainly look at for galaxy evolution research. And these are selected, they had in the recent billion years, a really strong starburst event where a lot of star formation happened. And afterwards, that star formation immediately ceased. Post-starburst give us a really good candidate sample to try to understand what mechanisms are making these pathways change. They're generally selected to not have current day star formation and to have intermediate age stellar populations. That means that we don't want really young stars or star formation, and we don't want only really old stars. So we can find something there in the middle. So compared to most post-starburst studies that usually look at right after the quenching event, the goal for my research has been to try to take one step back, to look a bit earlier, to look at the violent processes where quenching might still be occurring. However, how do we find galaxies where such quenching might be occurring? What do we look for to find black hole feedback, for instance, as like a physical mechanism? And the main tool that we use are spectra. If you think back to the image of like white light hitting a prism and being split up into different wavelengths, going from red to purple or violet, Similarly, the light that we get from our telescope from a galaxy target can be split up into different wavelengths, and we get this form of a spectrum. It's basically the accounting in a galaxy telling us what's happening there. Different emission lines that we can see here tell us what heated up gas might be inside of the galaxy. What type of stars do we see? It's very informative of the overall signature of what's happening there. The emission lines, if we take ratios of them, are incredibly useful to understanding the power sources that we're seeing in galaxies and if we see black hole feedback. When we take line ratios of highly ionized emission lines versus lower ionized ones, which the only difference being ones that maybe black hole feedback would cause for star formation, we see that there's a very big, distinct group where you have two populations. You have star forming, like on that red track, and you have black hole feedback as a power source there on that just gray mixing sequence offset. So diagnostic diagrams can be used to tell us what the different engines and power sources that are dominating ionization and like heating up of gas is in a galaxy. So compared to in 2016, Alotalo proposed creating a catalog of post-starbursts that also use this diagnostic criteria to look for galaxies that might have black hole feedback. So similar to other post-starburst studies, where you're looking to make sure you have intermediate age stars, but also you're looking to see if there's any black hole feedback by just making sure that we don't go on that star forming track in the dark gray. Her selection criteria resulted in a group of 1,000 shocked post-starburst galaxy candidates. We call them SPOGs, which are really interesting for us to look at. Follow-up observations of SPOGs have shown that they contain normal amounts of gas, but that they don't have much star formation, which would be strange because normally gas would condense down to create stars. So some quenching process might be occurring. They show signs in their centers that they contain neutral winds, and that's from data taken from the Sloan Digital Sky Survey, where if you see that really small red rectangle, it's more or less the size of the square where we have data. To tell if we actually see winds pushing gas out, we would need really spatially resolved information. And that's the main crux of where my research starts with the LDT. We need detailed spatial spectroscopy to see if we see any winds coming off of the galaxies or if we see quenching signatures. For quenching, if you look at the bottom row of galaxies there, the middle three in their centers seem to be a bit redder and a bit bluer on the edges. We want to confirm if there's a difference in star formation there to see if we are seeing this inside-out quenching model and if it might be caused by galactic winds. So that's where my observing campaign with the LDT began in 2019. We've been using the Devaney spectrograph to observe the SPOGs catalog. Out of the 1,000 initial ones that need follow-ups like spatial spectroscopy, we've observed about 90 of them. We observe along the minor axis, looking for heated up gas that is being pushed out of the galaxy, known as ionized gas, or for just molecular gas that is an ionized neutral emission. Along the major axis, we want to see if the spectra have different radially outwards star formation rates or such. So the data that we get from the LDT is 2D long slit spectroscopy, where similar to the one-dimensional spectra that I showed earlier, we have a wavelength dimension along the x-axis. Unlike it, we also have spatial information along the y-axis, which tells us above and below a certain pixel what we're seeing spatially. So we can tell if we're seeing winds outwards. And if you can tell from that image, in the really center, we have a really bright bar that is in like light yellowish. That's the galaxy at different wavelengths. At specific intervals, you have like H alpha, where you see the gas extending further. This is what we're looking for gas that is outside of the galaxy. But we don't really know what might be causing that. What might be causing it to be kicked out. We need these diagnostic diagrams I showed earlier to kind of tell. So first we take the data that we get from the LDT, throw it through a Python data reduction pipeline that I've been writing since 2019, and get data out. So generally, even in the SPOG sample, we're not going to see a lot of extraplanar emission. So here's an example galaxy where you see heated up gas, but it's just in the center there, nothing really outside. However, we're also seeing a significant portion of galaxies that have gas that has been kicked out, that is outside. For this example, it's even in this galaxy that's denoted by those red dashed lines, you see that it's skewed towards one edge. It's clearly being pushed out of the galaxy. However, that requires us then to ask, well, what is potentially causing this? And what to tell that, we use diagnostic diagrams from before. So we can spatially take emission lines for each row of pixels and plot each point on this diagnostic diagram. Here we're taking, I'm showing specifically those points outside the galaxy in the purple circles in the bottom left graph. And in the top right graph, there you see those extraplanar points also circled, which are triangles. And what we can really tell is that black hole feedback is what is causing that gas to be pushed out of the galaxy. It is incredibly powerful and seems to be what is the main driving mechanism. So overall, for my sample, there's a few questions that we're in the process of answering. Do we see ionized extraplanar gas? Yes. We're in the process of characterizing it, analyzing it, and really talking about it. So we're in the process of writing a paper on that. Next, we're going to be looking at neutral gas to see if there's any being kicked out also. And then we're going to be looking along the major axes to see if star formation is changing for these galaxies. But overall, this is a very spectacular for us to observe, which are really interesting and could give us really good insight about galaxy evolution.
Well, that's great. Thanks for that introduction. So the work that you're doing, you mentioned that you're writing a bunch of Python. You've been doing that for several years now. Are many other people doing this, or is this a new technique that you're using?
I'm using, it's just a general data reduction like Python package. Mm-hmm. So when I first started work, we didn't really have a data reduction pipeline to take raw data from the LDT for Devaney. I think in general, when you look at the field currently, a lot of data you would take and reduce yourself. We're in the process now with like major telescopes, I think, of creating these Python packages for like this age to be able to like reduce galaxies fast. Generally, it used to be more of a single person thing. I spent a good amount of time working on a pipeline, but it really does just the general packages that normally you would find in older coding languages, but now just brought up to Python.
Mm-hmm. Okay. And so with the LDT, what makes it so appropriate for this, for the observations you're making?
Yeah, no, the LDT is perfect because of the spatial long slit spectroscopy that it has. We've been able to observe, so the sample goes up to a certain redshift, which is just how far away the galaxy is. We've been able to observe this like extraplanar emission out to about half of that sample. in terms of like how far away it is. The LDT has been fantastic in terms of characterizing spatially what we're seeing with these winds. So that is something that, yeah, it does well for us.
Have you done observations with other telescopes or just the LDT? For this specific work?
Yeah, currently we've just been working with the LDT. It does exactly what we need to. Yeah, you can always go for like something that is a super high resolution, more than like what we're capable of, but it's not really needed. What we want to tell is if we see signs of extraplanar emission that is a sizable chunk. We can go super in depth because of how low redshift and how close these galaxies are, but it doesn't really help us know more if there's only a little bit of gas. We want to see for a large sample if we detect gas at all. So the LDT has been perfect to maximize looking, since the sample was 1,000, being able to maximize looking at a large number of spogs and also just get the spatial information.
You voted to this up to this point?
Sorry, could you repeat that?
I was wondering how many observing nights have you devoted to it so far, roughly?
Yeah, that's a good question. I've been observing constantly since 2019. I started this project as a small thing that my advisor wanted us to potentially look at, and it's really taken over. Usually I aim for about 6 nights a semester of observing. Sometimes you end up with some nights where you get rained out or snowed out. Yeah, I think overall 12 observing nights per year, like 3 years, so 36 about. Yeah, I have a couple coming up. Have the 28th and 29th of this month, and then the 26th and 27th of December. So it'll be really cool because we'll have a lot of time then to continue.
Yeah, and we'll get to our other guys here, but just one more question. Have you been out and used the LDT, or is this all remote?
Oh yeah, no, our first observing campaign we did at the LDT. That was in 2019. After that, we did a few remote sessions, and then obviously because of the pandemic, we've switched to remote in 2020 since. But yeah, we have a good setup to be able to do it. This is actually the remote observing room that we observe from. So it's kind of my pseudo apartment sometimes.
Yeah, well, at least you got out there once to see the setup. I mean, remote observing is so efficient in so many ways, but at some point, there's still the coolness factor of being out there at the instrument and just seeing it in operation and seeing the observers and the technicians running it and everything.
Oh yeah, and especially because of how dark it gets. Because for my galaxies, because of how faint they are, we request dark time. So it's really like mesmerizing, seeing like not being able to see even like your hand in front of you, and seeing like the full Milky Way above you. It is fantastic.
Yeah. Well, we'll talk about that a little bit more. Maybe just some of the awe you guys feel of doing astronomy. But let's jump ahead to Grant. And hear about some of your research. Grant Donnelly is a third-year graduate student at the University of Toledo. His advisor is Dr. J.D. Smith, and they study galaxy evolution, and they do that by observations of material in interstellar medium. Lowell Observatory has kind of a long connection to interstellar medium. Well, Lowell has a long connection with galactic studies in general, going back to VM Slifer, and studying what we call today galaxies and detecting redshift for the first time. But also with interstellar medium, he's also the one, interstellar gas and interstellar dust. He's the one that proved their existence because he was developing these new techniques done because the exposure was so darn long for so much of this. And so he really revolutionized a lot of that. So you guys are kind of standing on his shoulders and continuing those studies with more modern instruments and everything, but it's neat to make that connection through time and how that research in a different capacity maybe, but it's still continuing. So Grant, let's hear about your research and your work with the LDT.
Okay, yeah, so I'm Grant Donnelly. Thank you for the introduction. So at Lowell a long time ago, like he was saying, they would observe dust, probably, I'm guessing, through its attenuating effects, where it's blocking the stuff on the other side. We're lucky now in the 21st century that we can actually see the emission from dust itself, although you pretty much have to go up to space to do that really efficiently, but I'll talk about at the end how this ties into work with LDT. So the first thing I want to talk about is how a lot of people have this conception that the space between stars, or what we call the interstellar medium, is completely empty. It sure looks that way when you look up in the sky, all you can see are stars. And if you were somehow transported out to the space between stars, you wouldn't really find much there. But when we do look at images of galaxies, we can definitely see that that space is not empty. So what you're seeing here is one of the most recent images from the new James Webb Space Telescope, which is an infrared telescope. So it looks at light that you can't see with your eyes. It's like redder than red. And this is a type of light that the stuff in the interstellar medium, which we typically call dust, although there's also gas, that dust emits in the infrared light. So on this left image, you're seeing a Hubble image looking at light that you can see with your eyes. And on the right is a new image from Webb in infrared light. And you can see on the left image what's glowing. These are stars. And then the dark parts in between, that's the dust and gas that's blocking your view of the other side. And when you go over to the Webb image, it's exactly the opposite what you see. The bright stuff in the infrared is exactly the places where you're seeing the dust on the other side. So truly the space between the stars, there's a whole bunch of stuff going on there, and that's what I'm interested in. There are lots of different types of things in that interstellar medium. The type of thing I'm particularly interested in are these polycyclic aromatic hydrocarbons, big, long, fancy chemistry name, but in astronomy, we leave the chemistry to the chemists more or less, and we just take the name PAWS, which I'll use from now on. But all you really need to know is that they're molecules that look like this. Think large molecules, very small dust grains, made up of hundreds or thousands, or maybe a little bit more, of carbon atoms, like these gray things linked together in these cycles. That's where the polycyclic thing comes from. And then they have little hydrogen atoms sticking off at the end. Those are the little white dots there. You find these almost everywhere where you look in space, in almost all astrophysical environments, including the interstellar medium. And they make up around 15% of the carbon that you can find out there in space between the stars. So how can you actually see these things? Obviously, they're way, way too small to see with your eyes or even with a telescope directly, but we kind of can see them indirectly through the light that they emit. So these things are these PAWS are hanging out in space, and then you'll have these hot young stars nearby emitting light in visible wavelengths and ultraviolet wavelengths, more or less energetic light. And that the PAWS are good at eating that light. The light shines on them and it heats them up. And they start to do this little dance that you can see here, where all the atoms are sort of bending and stretching with respect to each other. And as they do that, they emit heat, which is infrared light. You can see that on the right there. Longer wavelengths, like the type that the James Webb Space Telescope sees. So here's an image of a galaxy. It's called M88. The light that you're seeing here, you wouldn't be able to see with your eyes. It's infrared, which is why I've colored it red to represent it so that we can see it. But the light that you're seeing here is almost entirely light that is coming from these PAW molecules. So you can just see how chock full of the stuff galaxies are. Around a fifth or 20% of the total infrared output of a typical galaxy will be just from these PAW molecules. So the important thing about pause, they're easy to see. They're so bright, like you can see in that image there, and they're extremely sensitive to their environment. And these two things added together means that they are very useful as diagnostics for astronomers. So we can tell about the environment that the pause are living in by looking at how the pause are reacting to things. So it's not just one wavelength of light that the pause will emit in. They have a whole spectrum. This is like a middle infrared spectrum that you're seeing here from about 5 to about 20 micrometers of wavelength. And you can see these little peaks that come out in the spectrum. And the ones that I've shaded in gray here, these are some of the major PA bands, places where PAs are throwing out all of their light that are very easy to see. So we have a whole spectrum in that mid-infrared. And for most of history in astronomy, a lot of attention has been paid to places other than this section of the entire electromagnetic spectrum. So on the left, you can see the blue, which is corresponding to hot things like stars and galaxies, and a whole bunch of time has been spent trying to nail exactly down how this works. And the same with the red, where you're seeing hot dust that is much, much larger than pause, and you have a whole bunch of effort going into that. And up until fairly recently, the PA spectrum, which you can see in the green there, has been sort of neglected. We have sort of like a template PA spectrum that's like an average of a whole bunch of galaxies that you see, and it's kind of just smacked right there in the middle with not too much thought given to it. But we're now seeing recently that the relative strengths of those peaks in the PA features can tell you a whole lot about what's going on with the actual molecules. And I'm going to show you that here. Did I skip a slide there? No, okay, cool. So what I'm particularly interested in is what Antoniu was talking about before, which is the supermassive black hole at the center of galaxies and how they relate to these PA molecules. So like he was saying, sometimes those black holes are accreting so violently that they throw a whole bunch of energy back out into space. And sometimes they're able to be as bright as their entire galaxy, the galaxy is around them, and sometimes they're like 1,000 times brighter than their entire host galaxy. We call these AGN, active galactic nuclei. And what we see when we look at galaxies that have an AGN, because not all of them have them, is that you get these weird PA spectra in galaxies with AGN. So in this plot on the left, the vertical axis, the y-axis, is showing you a shorter wavelength PA band, like 7 micrometers, divided by a longer wavelength PA band, like 11 micrometers, just as like a short to long ratio. It's a sort of a rule of thumb we can see to judge the shape of a PA spectrum. The red triangles are galaxies that have AGN, and the blue ones are normal galaxies with no AGN. And you can see that the red triangles like to hang out in the space below the blue triangles. So we have this suppression of shorter wavelength PA features compared to longer ones. You can see the same thing in this bar diagram on the right here. Same colors mean the same things. But now we have the short to long wavelength ratio on the horizontal axis here. And once again, the AGN like to have lower values of that. And so our job is to try and answer the question of why is that? And what can the PAs tell us about the environment of AGN galaxies by looking at these weird spectra? So I'm looking at one particular galaxy right now, which I found to be most interesting to me. NGC 4138 is its very creative name. But it's of particular interest because it's sort of this bulge in a center of old red soft light stars with an AGN in the center that you can't really see in this picture. And then there's this star-forming hot ring that goes around the bulge at around 1.5 kiloparsecs away. And I have this there's this other space telescope that preceded Webb that also looked in the infrared called Spitzer, and it took a big spectral map in the shape of this yellow square here. So anywhere I look in this yellow square, I can get a PA spectrum out of. And you can see I've drawn two circles, one a little black circle by the nucleus and a red circle in the star-forming ring there. And you can see the corresponding spectra at those places on the right. These two gray bars, you can call those the short bands, and these two are the long bands. And you can see that the black spectrum, corresponding to the center of the galaxy, has smaller short bands compared to the red spectrum. That's that suppression we're seeing on display in the AGN galaxy. So if you divvy it up more than just those two rings into little sections as you step out, you can see a whole profile of this 7 micrometer divided by 11 micrometer ratio. And you can see over here near the nucleus, you have the greatest suppression, and then you start stepping out of the galaxy and you get ratios that are much more similar to normal star-forming galaxies away from the AGN. And so it looks like the AGN has something to do with what is going on with the pause. So what are some of the ways that we might be able to explain this? So this is a plot that can take a little bit of time to disentangle, but there's one very just quick, interesting thing I can show you about it. On the vertical here, you have how good a certain PA is at radiating in a certain wavelength. And on the x-axis, you have the size of the PA. All of these little humps here correspond to a particular band, like that 7 micrometer up here, or the 11 micrometer down here. And you can see that PAs of different sizes are good or worse at radiating in these different bands. So like the shorter wavelength, like 6 and 7, smaller PAs like to emit in those. And the longer wavelength ones, like 11 and 17, larger PAs like to emit at those ones. There's also a difference between whether or not a PA is neutral or ionized, meaning if it has a charge or not. The upshot of all of this is those short wavelength bands are better at being radiated by small and ionized PAs, and the longer wavelength bands are better at being radiated by the large and neutral PAs. This can tell us potentially that in AGN, because you see that band ratio suppression, the AGN might be changing the sizes of the PA molecules in the galaxy. So here is an example that's often used of the distribution of PA sizes. This is just size on this axis, or how many of them are on this axis, and size on this axis down here. Smaller PAs being more abundant and larger PAs being over here. And the prevailing idea for what's going on here has been that when you have an AGN, PAs that are smaller and have a lower heat capacity are not good at withstanding the hard radiation coming from an AGN. They sort of blow them apart. And so as you step out radially from an AGN, you sort of start to lose all of those smaller PAs. And you aren't as good at radiating in that 7 or 11 or that 6 or 7 micrometers anymore. It's also possible that the ionization is changing. Remember, I showed how the charge of the PA, whether it's neutral or charged, changes the types of bands that it likes to radiate at. So we can make fancy diagrams like this, where we can try and track what is happening with the size and ionization by looking at those ratios. But the most important thing I'm trying to get across here is that by looking at the shape of the PA spectrum, you can really tell a lot of things about the conditions that the PAs are experiencing in their certain area of the galaxy. So how does this relate to the LDT at all? I've been talking about looking at PAs in infrared light. That's very hard to do from the ground. Not a lot of infrared light likes to come down through the atmosphere. The shortest wavelength PA band is at 3 micrometers, and the LDT and most ground-based telescopes when they look in the infrared, can only go out to about 2.5 micrometers. So you're not really getting any pause there. However, you can use the LDT to look at the conditions that could be causing pause to be the way they are. So the color of starlight is also potentially an important thing that affects the shape that you get from the spectra of pause. If you have like young 3 million year old stars, they have lots of high energy blue light that they're giving pause, making them maybe look like they're smaller than they are. On the other hand, if you have redder, older stars in like the bulge of a galaxy, they're going to be giving you light to the pause that make them potentially look like they're larger. For example, when you look at that ring galaxy, the bluest light you get is in that young star forming ring. And it really kind of seems like the pause know where that is, as their band profile sort of reacts to it. So next year, this year I put in a proposal to use the LDT and got some time on it that I will be using next year in the first half of the year, where I'll be using the same instrument that Antoniu is using, the Donnelly spectrograph. And I'm going to be placing the spectrograph at different angles on a whole bunch of galaxies, including the ring galaxy, like I've been showing you, and mapping the starlight conditions that are incident on the PAW molecules. And I can use the spectra that I get to learn about what the type of starlight is in that region. And then I can compare it with that Spitzer data, like I was showing you, to see if it seems like it is the starlight rather than the AGN itself that is making the pause behave the way they are. All right, yeah, I think that's it.
Well, thanks, Grant. With you mentioned that you're able to study, you're looking at the conditions of the pause. Are there other techniques looking at the same result? And how does what you're doing compare with what others are seeing?
Yeah, so this suppression of the short wavelengths has been seen for a little bit over a decade now. And in almost everywhere that you have looked, that people have looked for pause and noticed whether there was an AGN or not in a galaxy, they have seen this suppression. Basically everywhere that we've looked, we've seen this. It hasn't been really done so far that you can step in from the center of a galaxy out and look what they look like. We're kind of doing that for the first time more or less. And now that we have Webb, the James Webb Space Telescope, which is looking at basically the same wavelengths that Spitzer looked at, there's a real renewed interest in these types of molecules because they're one of the brightest things you can see with the new fancy space telescope. And we've had a lot of fun talking about, or talking to people who have never looked in the infrared before, who are suddenly very interested in these things.
Mm-hmm. What initially got you interested in studying pause? I mean, they're so important, and in fact, some people might remember the Martian meteorite back 25 years ago, that there was suggestion that it might have had some fossil life, and they were looking at the pause in there. How did you get interested in that particular angle?
I actually wasn't really aware of them before I came to the University of Toledo. And then I was always interested in things happening in the infrared, but I wasn't super aware of these specific things. And as you go and talk to the faculty and try and figure out who it is that you want to have as your advisor, you sort of start reading all of their papers, and then some of them really stand out to you. And this just presented itself to me as a really interesting problem because there's just so many open questions we still have about it.
Well, it must be exciting to be able to answer some of those questions.
Yeah, so this is a paper that is wrapping up pretty soon, and then the next step is to move on to a larger sample. We still have lots of Spitzer data that we're still cleaning up, and then hopefully Webb time, where we can use Webb's spatial resolution to just look right in the nucleus of a galaxy.
And that's a good point you're making, that, you mentioned several different telescopes, Spitzer, Webb, LDT, and different telescopes have different instruments and do different things, or do them in different ways. So it's not unusual to use several different instruments to really analyze whatever you might be looking at.
Mm-hmm. Yeah, it's just looking at the problem from all angles, right? Mm-hmm. It's easy to get like blinders on when you're using one particular instrument and one method, and as soon as you use something in a different wavelength regime or something, you can see everything from a whole new perspective.
Yeah, that's great. Okay, well, let's move on to our last presenter, Sam Federman. Sam's a fifth-year graduate student, which means, I think that means that soon you'll be celebrating a PhD. Hopefully that you can fill us in about that. But he's working a PhD in astrophysics at the University of Toledo with his advisor, Tom McGeeth. You'll have to correct me on that. And they're studying the formation and evolution of young stars. So this is great because, again, astronomy, there's a certain number of people working in it, and some of the Lowell astronomers are formation evolution as well as galactic studies. Not quite the same as what you guys are doing, but looking at some of the same questions and trying to come up with some of the same answers about formation and evolution and what's it mean compared to other systems. So Sam, thanks for being here, and let's hear about your research.
All right, hopefully you can see the screen here. So I want to thank everyone for the opportunity to be able to speak today about my research. I'm a fifth-year grad student at the University of Toledo, and my work focuses on the formation of stars within our own galaxy, whereas Grant and Antoniu are focusing much more on star formation and galaxies outside of our own. And so here you can see just an example image of a protostar with some of the typical features that we see, including a beautiful outflow cavity, which I will talk more about. So I should start by defining what a protostar is, and it basically is a baby star that is still growing in mass. And they start off in giant clouds of molecular gas and dust that are floating in the galaxy. And gravity causes denser regions of the cloud to collapse, and eventually the gravity collapses to a sufficient point that a protostar is formed. That protostar is surrounded by an envelope of material that is falling onto the system and feeding it mass. But that infalling material also therefore powers outflows. And the interplay of this infall and the accretion onto the source and the outflows regulate the ultimate mass of the star. So here we can see an image in visible light. We see red showing all the molecular material that is inside the Orion cloud. You can see the shape of the Orion constellation here. The green stars that you see, those are all dusty young stellar objects that are embedded within the cloud. And in blue, you can see the outline of the Spitzer coverage from our survey. And in the white stars here, you can see are very massive, very bright stars that we call OB stars. So as I mentioned, the star formation process begins with the collapse of denser regions inside molecular clouds. And so eventually gravity causes this material to condense until you get a central protostar. And this protostar is surrounded by an envelope of material of dust and gas, which is falling onto it. And because angular momentum has to be conserved, that eventually material that flattens into a disk surrounding the star. So that's what you see here in this panel C, is a dusty envelope falling onto a disk. The disk is what actually transports material onto the star, and eventually magnetic fields take the material from the inner edge of the disk onto the star. And they also, that powers outflows, which launch outwards and carve cavities in the envelope. So this whole process can take roughly around 100,000 to 200,000 years. And then eventually the envelope is cleared and you're left with just a disk and a central star and the outflow. And as that evolution progresses, eventually accretion turns off and the star stops growing in mass. And you're left with a dusty debris disk in which planets can begin to grow and form. And finally, in a few million years, give or take, you have a central star surrounded by whatever planets were formed, and it can happily live its life according to its mass. So to study protostars, we have to utilize all of our available tools. And you've heard in the previous talks about using different wavelengths of light. So I've shown here a diagram. The visible light that we see is only a very short part of the spectrum. And there's light that has much higher energy and shorter wavelength. And there's also light that has much lower energy and longer wavelength. And so to see protostars, we have to actually utilize those longer wavelengths because at visible wavelengths and shorter, they're too deeply embedded and the dust obscures them, just as we saw in the pictures of the galaxies, those dust dark lanes that obscure the starlight. So using this infrared light and longer wavelength, we can measure the light that's coming out at different wavelengths to construct what's called a spectral energy distribution, which is basically just a spectrum. And that allows us to classify and fit models to understand the nature of the protostar. But one issue is that these are three-dimensional objects that we're seeing in a two-dimensional projection. And so the inclination of the source towards or away from you can have an effect on what we see in the spectral energy distribution. So to highlight this, I'm showing now a visible light image of the Orion molecular cloud region, and you can see all the bright stars, but most of it is obscured by all this dust and material that we can't see through. However, if we move to the infrared, suddenly you see a huge wealth of stars all throughout. And this is why we need to use the infrared and longer wavelengths, because the dust simply obscures it too deeply if we look at shorter wavelengths. So when we're looking at protostars at different wavelengths, we're actually looking at different parts and different processes. So what I've shown here is a simple progression of a single protostar, the same protostar in different wavelengths. So if we start with the Hubble at the shortest wavelength, you can see a scale bar. This scale bar is the same across all the images. So in the Hubble image, we're seeing a central source and a beautiful outflow cavity being carved by the outflows. And then as we move along in wavelength, we're zooming out because our wavelength is getting shorter. And so we're covering more of the surrounding molecular material. My work has focused on this bottom panel, which is a comparison of two relatively higher resolution images using sub-millimeter wavelengths, or just wavelengths just under 1 millimeter in wavelength. And so you can see in the image on the left is an envelope, a dusty envelope surrounding a protostar. And then deep down in the center, if you can barely see it, is a disk. And that is the protostellar disk that is feeding material onto the protostar. And so my main focus for much of the beginning of my career here has been on using sub-millimeter wavelengths to study protostellar evolution. And so in the sub-millimeter wavelength regime, we're looking at cold dust, the continuum from that dust as it gets heated up to around 15 to 30 Kelvin. And we find that in astronomy, when you have a bigger telescope, that allows you to have a better spatial resolution. There's a simple relation where your resolution is roughly comparable to the wavelength of light over the diameter of your telescope. So a bigger telescope is better for your resolution. However, building really big telescopes is expensive and hard. So what we do instead is use pairs of telescopes in what is called interferometer arrays. And these can be set at a distance to simulate very large aperture telescopes. And so my first work focused on using the ALMA array in Chile. And so you can see here, there's actually two arrays. There's a large array, which is the 12-meter array, and there's a more compact array over here, which is called the ACA. And so my paper, which is now on archive and will soon be published in the Astrophysical Journal, was using a comparison of this relatively medium resolution ACA data to the higher resolution 12-meter data. And that allows us to probe the relative contribution of the disk and the envelope. And so what this means is that as protostars evolve, those outflows and the infall of material dissipate the envelope, and the disk comes to shine more clearly through in the submillimeter and dominates the flux. And so what we found is that this comparison actually is a more reliable method of gauging the evolutionary process for individual protostars compared to more traditional methods that have been used previously. And so if you want to learn more, I highly encourage you to read my paper, which is on archive at the link listed, and I'd be happy to answer any questions that you have. Before I finish up, I want to talk about my current work, which is using brand new James Webb Space Telescope data to measure protostellar evolution at much shorter wavelengths in the near infrared. And so this is part of the program that we call IPA, which is investigating protostellar accretion across the mass spectrum. And so this program has 5 targets, which are young protostars, and they have a range in masses from 1/10 to 12 times the mass of the sun. And they have a brightness that is up to 10,000 times the power that the sun puts out. And so we are going to use this revolutionary telescope, James Webb, to analyze the near to mid-infrared spectra and to pick out signatures of accretion and outflow, which we can use to distinguish from models. And so what I hope you learned is quite simple. Stars are born from the collapse of gas and dust in molecular clouds, and the ultimate mass of a star, and therefore its fate, is determined by the interplay of infall of material, accretion onto a protostar, and outflow powered by that accretion. And in order to do this properly, we need to study protostars across the electromagnetic spectrum. And the latest introduction to that would be with James Webb using the near infrared and mid infrared to totally revolutionize our understanding. And I'll just plug my paper one more time. I really hope you read it if you get an opportunity. And I'll be happy to take any questions that you have.
Okay, thanks, Sam. Something that strikes me is, you know, you guys are students, you're working toward your stand. That doesn't mean you're waiting in line until sometime later in your career to use some of the best telescopes in the world.
It's really been
James Webb, Spitzer. It's, you know, being part of a university like Toledo, and have collaborations like with Lowell and other, and that's a pretty neat thing it seems like, to be doing, you know, somewhat early in your career.
Absolutely.
Well, this is great. What a nice diversity of research you guys are doing. I mean, there's some similar threads, of course, but using that Davini spectrograph on the LDT for looking at stuff both within and outside of our galaxy. And it really represents the LDT. You know, this year we've been talking about the research with it, and it's stuff from the inner solar system beyond our galaxy. And it's such a diverse instrument, especially when you look at the instruments package that's on it. And so it's nice to be able to hear from you guys and hear about your research. And we look forward to talk with you down the road again as your careers develop and see where your research is taking you. So let's, we've got just like a minute or so, but we got a couple of questions that we didn't get to yet that I thought we'd ask. One is from Jasmine, the timeline on the starburst changes, maybe in light years or whatever appropriate unit. So I think, Antonio, if you can probably, is that you?
Yeah, I think starburst, right? Yeah, so it's usually starburst occurs in what we want to look at in like the last 1 billion years, and it ends pretty abruptly after that time, where we can detect starbursts like in the last billion years, basically.
Mm-hmm. Okay, and it looks like, we're at 8 o'clock, but we'll get one more question. First of all, if we can share a link with your paper.
Oh, yeah.
Sam.
I should
And if
definitely.
you put that in the chat, then our team can get it in the YouTube chat. And then while he's doing that, one last farewell question. This was kind of an open question: the farthest object observed from your location, but maybe we can modify that a little bit and talk about the farthest thing that you guys have looked at, each of you, and we'll end with that.
Okay.
So you kind of have like a logarithmic scale of how far away we study things. So Sam is looking at things in our backyard, stars in Orion, which is only a couple hundred light years away, right?
Yep.
I look at nearby galaxies that you can see easily, nice and big, are less than 20 million parsecs, so like 60 million light years, something like that. And then there's Antoniu, who looks at galaxies that are much, much farther away, even with some redshift sometimes, right?
Yeah,
I'll let
yeah,
you
basically.
say how far away they are. I don't actually know.
Yeah, same. I know their redshift distance. So, yeah. Basically, though, way farther away than what Grant is looking at. Orders of magnitude of like 20 or 10.
Okay. And I believe Maddie is typing in the link to Sam's paper. And so I'll just talk for another minute or so people have a chance to copy that down in the comment section. Thank you guys for joining us. It's exciting to hear from astronomers in the front of their career. We certainly have heard from a lot of scientists throughout the year that in different stages of their career, but it's always exciting to think about what you're doing now and then come back in 5 years and 10 years and 15 and see, if you're along the same path, if you're doing different things, but how what you're doing now is really, informing your future. So good luck with it all down the road and winning us tonight. And thanks for our behind the scenes team of Nate and Maddie for keeping everything operating. And we'd like to thank our donors and sponsors who support this and other programs. And thanks everybody for watching. This is really fun to be able to celebrate something like the Lowell Discovery Telescope. And as we talked about, we're focused on the LDT, but this is part of a kind of a network of telescopes and scientists around the world, all working together to answer some fundamental questions about the universe around us. So it's a fun time to be able to talk about this stuff, and really great to have some up and coming scientists joining us. So thanks everybody for joining the program tonight. And next month we'll conclude our coverage of the LDT 10th anniversary. Dr. Stephen Levine, who's the kind of in charge of the LDT project scientist. I can't remember if that's the exact title. So Stephen, I apologize if I got that wrong. But one of the leaders in managing the LDT, and we're going to review kind of the top discoveries to date. And that's going to be hard to narrow down because there have been so much great research, and we certainly heard about some of that tonight. So thanks everybody for joining us, and we'll see you next time.
Thank you so much.
Thank you.